Flipped classroom video for Maths A2 Unit 3, applying the chain rule recursively. So, the further trigonometric functions, of course, are we've looked at sine, cos and tan, but now we need to look at sec, cosec and cot. So, let's have a look at sec x. Start off with y equals sec x, and recognise that sec x is 1 over cos x, so we can write it as cos x to the minus 1. And that means we have a chain rule situation, so we can let u equals cos x, du by dx is therefore minus sine x, y is u to the minus 1 because it's cos x to the minus 1 and cos x is equal to u. So we can differentiate y to get minus u to the minus 2, and then we can sub our cos x back in, so that gives us minus cos x to the minus 2. So to get dy by dx we need to do dy by du times du by dx, and that gives us dy by du is minus cos x to the minus 2 times du by dx, which is minus sine x. And we can faff about with these, so we first of all, the minuses cancel. Cos x to the minus 2 can go on the bottom, so that gives us sine x over cos squared x. We can separate them into 1 over cos x times sine x over cos x, and that gives us that dy by dx is sec x tan x. And you can see with that faffing about there are different ways we could write this, but that's a neat way and a sort of standard way of writing it. So in summary, if y is equal to sec x, then dy by dx is equal to sec x tan x. So moving on to cosec x, differentiating cosec x follows a similar method, pretty much the same method to that of sec x, and that leads to d by dx of cosec x gives us minus cosec x times cot x, and you can see that's a sort of similar result to the one for sec x, but it's negative, and sec has become cosec and tan has become cot, which is sort of not that unexpected. So there's the result, and you ought to have a go at deriving this yourself, and you can use the sec x differentiation on the left to help you if you need to work out the steps, but that's a good exercise to have a go at. Anyway, moving on to cot x, if y is equal to cot x, then it's equal to 1 over tan x, and that is tan x to the minus 1. So if we differentiate that using the chain rule, then we have to differentiate bracket to the power of minus 1 with tan x inside, which gives us minus tan x to the minus 2, but we also need to differentiate the inner function of tan x, so I've just put d by dx of tan x there. When we differentiate tan x we get sec squared x, so that gives us now minus tan x to the minus 2 sec squared x. If we write tan x as sine x over cos x, we then get that expression minus sine x over cos x to the minus 2 sec squared x. The minus sign means we flip it up and we can square the top and bottom of that fraction now, so we get minus cos squared x over sine squared x times 1 over cos squared x. We can see that the cos squared x is cancel, and 1 over sine squared x is cosec squared x, so finally we get the result of minus cosec squared of x. And so the final result is that if we start with y equals cot x, then we finish with dy by dx is equal to minus cosec squared of x. And notice again the analogy with tan, because when we differentiate tan x we get sec squared x, and so these relationships between sine, cos and tan continue when we differentiate the functions. There's some interesting relationships going on. Okay, so we'll now have a look at the recursive chain rule, and recursive means something that can be repeated or applied repeatedly, and we've seen before that if y is equal to f of g of x, then if we write y equals f of u and u equals g of x, then we can find dy by dx by doing dy by du times du by dx. And we can extend this. So if we now have f of g of h of x, then we can say that y is equal to f of u is equal to g of v, and v is equal to h of x, and we get that dy by dx is equal to dy by du times du by dv times dv by dx. So let's try using this idea to differentiate a nasty complicated looking function. Y equals sec squared of x cubed. Now actually it doesn't look that nasty, but in fact there are three functions in there. So if we think of what happens to a value x when we put it into this function, first it's cubed, x cubed, then we take the sec of what we have, so that's sec of x cubed, and then we square what we have now to finally give us sec squared of x cubed. So if we give the functions inside this function the letters, so we say that cubing x is the function h, and then taking the sec of that is the function g, and then squaring that is f, then we can write that y is f of u, which is u squared, u is g of v, so the function g is sec of v, and v is h of x, which is x cubed. Now we need to differentiate each of these to do our chain rule. So when we differentiate u squared, we get 2u. When we differentiate sec v, we get sec v tan v. And when we differentiate x cubed, we get 3x squared. So dy by dx is dy by du times du by dv times dv by dx. And by subbing in those separate differentiated functions, we get 2u times sec v tan v times 3x squared. Now we then have to gradually replace the u's and v's because we want everything to be x, and so we can replace u by sec v, so that gives us 2 sec v times tan v times 3x squared. I think at this point it's worth tidying up, so that gives us the 2 at the beginning times the 3 towards the end gives us 6, and we've got our x squared, and then we put tan v, and then of course we've got sec squared v. The order of that is a sort of conventional thing, wouldn't worry about it too much. But now we've still got a v in there, and we need to replace v by v equals x cubed. So that gives us our final result, which is 6x squared tan of x cubed sec squared of x cubed. And although it is possible to do this sort of differentiation sort of by inspection, this is a good way of making sure you don't make any slips, and it's a good way of understanding what's going on as well.